All right, welcome back to lesson 3 of our unit on solving exponential equations. This is the big one. This is the skill that should be relatively new to some people. Now, depending on which course you took last year and again, which teacher you took it with, you may have touched on these, you may not have seen them at all. I'm going to teach them assuming you're coming from scratch, but you may have seen them before. They're called logarithms, which we usually call log for short, and they are used to solve exponential equations. Now, I'm going to talk more about this later, but the idea of opposite operations, you've learned that way back in like grade 2, I think, or grade 1, that plus and minuses are opposite operations. Adding numbers and subtracting is the opposite. Multiplying and dividing is the opposite. Squares and square roots are the opposite. And it turns out that there is an opposite to exponential, and that's log. So it's basically taking us backwards. We'll see how to use it, but first I want to do a couple other things to kind of work up to that point. And I do want to remind you that despite the fact that we're going to learn how to use these logs to solve problems a little bit faster and more efficiently than other methods we've used so far, you're still expected to know those other methods like the trial and error that we're going to use in this question. So if you use logs on the test, the question will actually say solve using trial and error. If you use logs to solve it, you are not answering the question, even though you're getting the numerical value correct. So let's jump into this example and use what we did the other day of trial and error. Here we go. The percent of medicine in a person's bloodstream T hours after receiving a dose can be modeled by the function m at t equals 100 times 0.71 to the exponent t. So that's the amount of medication at time. It starts off at 100% and it's going to tick down over time. So it's basically losing 29% of its value every hour, dropping from 1 to 0.71. Doctor doesn't want to give the second dose until they are only 15% of the medication remaining because they don't want the patient to overdose. How long must the patient wait before getting a second dose? Incidentally, I was on a medication several years back and I took the second dose of my medication a little bit earlier than I was supposed to because I was really feeling sore and I thought my heart was going to explode. So it is important that you make sure that you're not putting too much into your system at one time. All right, so we're going to just set this up and say we want the amount of medication in our system, M at t, is 100 times 0.71 to the t, and we want it to be down to 15% before we get our next dose. So that means 15 equals 100 to the 0.71 t. Divide both sides by 100. 0.15 equals 0.71 to the exponent t. And if you recall the trial and error method, I feel bad we're using trial and error on medical grade stuff, but anyway, we guess a t and then we plug in 0.71 t. Plug it into 0.71 t and our target number is 0.15. So again, you can guess what this is. It doesn't look like it'll take that long if it's dropping off at 29, basically 2/3 of the amount every hour. I'm just going to throw out a guess there of 4 and see how close I am. Just because I know a lot of medications wear off after about 4 hours. So 0.71 to the exponent 4 is 0.254. Okay, well that's still a little too much medication in our system. We want to get it down to 0.15. So what I'll do is I'll try maybe 5 hours. 0.71 to the exponent 5, that gives us 0.18. 180. 6 hours, since we're still a little too high. 0.71 to the exponent 6 is 0.128. Okay, so 5 hours is the closest, but it's still a little bit too much. And I think maybe we should be more specific than just, 1 whole hour. Maybe we should get down to like 0.1 hours. So looking at these, the 0.15 seems a little bit closer to the 5 than the 6. Actually, That's not much different. I'm going to try 5.5. So 0.71 to the exponent 5.5 is 0.152. And that's technically still just a little bit over what we want the target of 0.15 to be. So maybe I'll try 5.6. We don't want to kill our patient just in the first question. 0.71 to the exponent 5.6 is 0.147. Okay, so it's between 5.5 and 5.6 hours. Again, 0.1 of an hour is about 6 minutes. Well, it's actually exactly 6 minutes. So, you know what, if we're somewhere between these, 5.5 hours is 5 hours 30 minutes, 5.6 is 5 hours 36 minutes, probably around 5 hours and 33 minutes, 5.55 hours. But either way, I think that we're within a 6 minute mark now. I think that's probably close enough. So we'll say that t equals, let's just round up to 5.6 to be safe. So again, we don't kill our patient. And that's hours. Okay, so that's how we solved it using trial and error. We basically simplified the equation just a little bit so that we had it in the form of number equals number to an exponent. We plugged in our value, our guess for t. We figured out what 0.71 to the t was, and we were shooting for 0.15. I wouldn't consider that to be a huge waste of time. It's not that time consuming to do that, truthfully. Again, we had to do 5 guesses, but each guess took us very little time to complete. It was mostly just me blabbing on. Right, before we continue on to our new method, I'm going to point out that when we solve equations, we do the same things to both sides. I know we've talked about this before, but I really, really want to emphasize it. This one, as opposed to the previous couple lessons, I'm going to do in extra steps to show you that we are in fact doing the same thing to both sides. So to solve this 3x plus 7 equals 22, what I'm going to do is take 3x plus 7, leave a little space, and I'm going to show you I'm just subtract 7 from that side, subtract 7 from that side. And that simplifies to 3x equals 15. And then I'm going to write 3x divided by 3 equals 5, 15 divided by 3, and that's x equals 5. So anytime we do something to one side of the equation, we have to do the same thing to the other side of the equation. We need to keep that in mind because when we're using logs, we have to do the same thing. If we log one side, we have to log the other. We cannot leave the other the same and just log one side. And a lot of people have a tendency to do that. All right. What I would like you to do is take a moment without me giving you the answers. And I want you to find the log button on your calculator. It's probably up at the top somewhere. It could be behind a second function or inverse, but it's probably its own button. And it just says log. Now, for those who have seen this before in some way, shape, or form, you'll notice that there's another button beside log that says ln. I do not want you to touch the ln button at any point in this course. I will not accept ln on the test. I will not mark ln. I know that it can be used to solve these questions, but we're not going to. We're only going to use the log button. I want to be super clear on this. If you use the ln button, no marks. Okay, so once you've isolated the log button, what I'd like you to do is punch in log of 10. Now, depending on your calculator, you may have to hit the log button first and then enter 10 and hit equals. Or if you've got the a different type of calculator, you may type in the 10 first and then hit the log button. A good way to check which one it is depends on how you punch in numbers like the square root of 25. If you hit the 25 and then hit the square root button, then you're going to do 10 and then the log button. And if you do square root and then 25, then you'll probably plug in log and then 10. Either way, when you do this, the log of 10, the answer should be 1, which is not very exciting. But what I would like you to do is once you verify that that is what you're getting using your calculator correctly, I'd like you to just take a moment, and I'd like you to go through the rest of these and just write down what you get. I know that I could just as easily show you the answers to them because I can do them very quickly and easily. But this is one thing that if you see the pattern on your own, your brain will remember it better. You will have a better understanding of logs than if I just tell you what the result is. So take a moment, pause the video, fill those 5 numbers in if you haven't done so already. And when you're done that, come back and check the answers. Alrighty, so these are the numbers you should have gotten. And if you looked at them and you recognize what the pattern is, it's essentially the number of zeros you see before or after the 1. So log of 10, there's 1 0 after the 1 in the 10. 1,000 has 3 zeros after the 1. 1 has no zeros after the 1. So the log of 1 is just 0. If you have 0.1, there's actually kind of like the decimals move the other way, so it's -1. For 100,000, we have 5 zeros. And in F, we have to move the decimal place over 3 to put it back after the 1 like it should be, so we say it's -3. Essentially what we're finding here is what exponent do we put on 10 to get the value that we're taking the log of. So for the first one, it's saying, what exponent do I put on 10 to get 10? And the answer is 10 to the exponent 1, so 1. The second one's saying, what exponent do I put on 1,000? Or sorry, what exponent do I put on 3 to get what exponent do I put on 10 to get 1,000? And the answer is 3. What exponent do I put on 10 to get 1? Well, 10 to the exponent 0 will give me 1, so the exponent must be that. This one is actually 1 over 10, so 10 to the exponent -1 will give me 1 over 10. 10 to the exponent 5 will give me 100,000. 10 to the exponent -3 will give me 1 over 1,000, which is 0.001. So basically, this is telling me what exponent I need to put on 10 to get that number. Cool. If you know the pattern, we can estimate these despite the fact that without a calculator, it's hard to get a precise value. So here's the way I'm going to look at it. I want to see which powers of 10 120 is between. So I'm just going to write it this way. And by the way, this is not a solution at all. It's just kind of a way of thinking about it. 120 is between 100 and 1,000. So it means that 120 is between 10 squared and 10 cubed. And it's closer to 10 squared. It's a lot closer to 10 squared. So what exponent do we put on 10 to get 120? Well, it's got to be between 2 and 3. The exponent we get on 100, the exponent we get for 1,000. So if it's between 2 and 3 and it's closer to the 2, I'm going to guess 2.1. Again, I kind of want this to not almost be there because it makes it look like I'm like evaluating something. I'm just putting down my thinking and then answering the original question of log 120. Now that's just an estimate, like the rough thing in my head. If I actually put 120 or the log of 120 into my calculator, it's actually 2.08, which actually isn't too bad. 2.1 is not a bad guess. Similarly, if I think about 8,000, 8,000 is less than 10,000, which is a power of 10, and it's greater than 1,000, which is a power of 10. So on the left, it's squeezed between 10 cubed. On the right, it's 10 to the 4th. This is closer to 10 to the 4th, so that when I take the log of each of those, it's between 3 and 4, and it's closer to 4. So I'm going to guess it's something probably like 3.8. Now, if I punch the log of 8,000 into my calculator, it's actually 3.9. Okay, but again, our estimate is not bad. We're basically just trying to squeeze it between two numbers. Okay, the log of 0.9. Now this is where it gets a little bit confusing with numbers less than 1. But we know that that's between 1 and 0.1. And it's obviously much closer to um, 1 than it is 0.1. Well, this is actually 10 to the negative 1, and this is 10 to the 0. And we know that 0.9 is closer to this one. So if we look at the exponents, it's between 0 and negative 1, or negative 1 and 0, depending which direction you want to think about it. But it's definitely closer to the 0. So I'm going to guess that it's more like 0.1 or negative 0.1 or negative 0.2. And if I put 0.9, the log of that, into my calculator, it's actually negative 0.046-ish. Okay, so was I off? Yeah, but I was still kind of between 0 and negative 1 and definitely closer to 0. And that's the best we could do, is basically squeeze it between two nice powers of 10. Likewise here, 0.03 is between 0.1 and 0.01. This is 10 to the negative 2. This is 10 to the negative 1. It's a little bit closer to this side. In fact, this is again where our brain doesn't do logs or exponents so well. Our brain's very linear. This one I think is actually going to be almost exactly negative 1.5. But either way, as long as you could guess that it's a number between negative 2 and negative 1, you'd be okay. And if I put 0.03 into my calculator and take the log of it, I get negative 1.52. So very close to that number. Now, for those who are wondering why 0.03 is kind of halfway between 0.01 and 0.1, even though it's 0.3, it's because you have to triple 0.01 to get to 0.03 and triple 0.03 to get to 0.1. Again, it's our brains think linearly, but this isn't a linear issue. It's an exponential issue. But the point is, as long as you can estimate the two numbers it's between, I don't care if the second digit's correct. It's kind of a wild guess, but you usually can get kind of it's either towards one number or the other. Okay, the next part here is what happens if we're dealing with bases that are not base 10. By default, the log button on our calculator always tells you what exponent to put on a 10 for the number you put in. But sometimes we don't want that. Sometimes we want to know what exponent to put on a 3. And our calculator doesn't have a button for log base 3. So we're going to basically switch it around a little bit. If you want to take a moment and look at this, for base 10, the log of x equals y means the exact same thing as x equals 10 to the y. So it's basically saying y is the exponent on 10 to get x. Here, if we have a general base, it's just saying that y is the exponent we put on b to get x. You'll notice that I call it log base b of x, and in exponential form, I say x equals b to the exponent y, where b is the base. The fact that I'm calling b the base in both cases is really a hint that that number is the same in both of those equations. When it's in log, the b is the base. When it's as an exponential, b is the base of the exponential. Okay, so that seems complicated, but let's just do a quick rewrite. So we have these in log form. I'm going to rewrite them in exponential form. And by the way, I'm not putting variables in these. I'm doing ones that work out nicely so that hopefully your brain will catch the pattern nicer. Log base 4 of 64 is equal to 3. Well, that's really saying the exponent I put on 4 is 3 in order to get 64. So the base of the log is the exact same as the base of the exponential. This is the exponent. This is the answer. So base exponent answer. And likewise over here, I read this as base exponent answer. So base exponent answer. And sure enough, that's true. This one, base exponent answer. All right, going backwards, we do log base 2 of 64 equals the exponent 6. For the second one, log base 3 of 1/9 equals -2. Again, -2 is the exponent. And here, log base 5 of 125 equals 3. So the part that's alone is the exponent. Part that's alone is the exponent. Part that's alone is the exponent. The bases are the same. That's why we call them base in both forms. And the number that goes into the log is the answer from the original part. So 64 was the answer. We plug that into the log. 1/9 was the answer. We plug that into the log, and so on. In order to evaluate logs of different bases, it's actually easier than you might think. So again, there's no button on your calculator for log base 2, log base 3, or whatever, but here's how we do it. And we can do these kind of manually. Sorry, I shouldn't say that. Let's do these ones by observation. I can rewrite this one to say, this is what exponent, basically, if I think of this as log base 2 of 32 equals x, I can say, what exponent do I put on 2 to get 32? So I'm just changing it from log format to exponential format. And then I just look at that and say, well, it's 2 times 2 times 2 times 2 times 2 is x should be 5. So no calculator needed for that. The next one is, what exponent do I put on 3 to get 81? So I'm converting from log form to exponential form. And my brain says 3 times 3 times 3 times 3 is 81, so x is 4. Of course, these only work because the numbers are working out nicely for us, but we'll see how to use our calculator in just a moment. This one's saying, what exponent do I put on 2 to get 1/8? And remember, that's really 2 cubed on the bottom, which means our exponent is going to be -3. 2 to the exponent -3 will give us 1 over 2 cubed, or 1 over 8. Okay, so that's flipping forms in order to evaluate them by observation without a calculator. But again, only works if the numbers are pretty. If the number that we're trying to shoot for is a nice power of the base, then we can do it. If it's not, not so much. But it turns out we can actually solve any base by just doing the log of what it is you're taking the log of divided by the log of the base if it's not base 10. If it's base 10, then we don't write the b there. It's just assumed to be base 10, and we don't have to divide by the log of base 10 because the log of base 10 is 1 anyway. So the good news is we can solve these super quick with our calculators. This just becomes log of 81, and you'll notice there's no base written there, which by default is base 10 or what your calculator uses. And we just divide it by the base that we had, the log of the base that we had. So we know that the answer should be 4. So when I type in the log of 81, I get 1.9, which is a lousy number. And I divide it by the log of 3, which is 0.477, which is a lousy number. And then I hit equals. It gives me exactly 4. This next one, log base 5 of 125. Well, I know the exponent I put on 5 to get 125 is 3, so that should be the answer. But if I want to use my calculator, I could just do log of 125 divided by log of 5. And both of those individually are horrible numbers. They're not pretty. But when I do that, 125 log is 2.0969. divided by log of 5, which is 0.69897. And sure enough, when I actually do the division, it's just 3. And then this one super quickly, log of 64 divided by log of 2. Just do those in your calculator and you should get out 6. Double check it to see that it actually does work. And yeah, it should. Okay, so now that we've kind of seen how the logs work, we can deal with ones that aren't so pretty to solve. For number 9, this first one I'm going to just try to do by observation. So what power do I put on 3, or what exponent do I put on 3 to get 70? I know 3 to the 1 is 3, 3 squared is 9, 3 cubed is 27, and 3 to the 4th is 81. So I know cube is too small and exponent of 4 is too large. So I'm expecting an answer between 3 and 4, probably a little closer to 4. If I actually plug it into my calculator, I just plug it in as log of 70 divided by log of 3. 70 log is 1.8 something divided by the log of 3, which is 0.47 something. And when I divide them, I get 3.867147,023. And I do not need to write that out every time. But my point is, we could at best kind of guess one decimal place when we were doing it with our logic. We knew it was between 3 and 4, closer to 4. I want to show you that this method, your calculator gives you the precise answer, or at least as many decimals as it can hold. Okay, the second one, again, before I begin it, I kind of just want to take a guess in my head of what it's going to be. 6 to the exponent 1 is 6. 6 to the exponent 2 is 36. So one's too small, one's too large. The exponent's between 1 and 2, so the answer should be between 1 and 2. So I'm expecting something maybe around 1/2. So log 21 over log 6. Log of 21 divided by log of 6 equals 1. Oh, sorry, did I say 1/2? No, sorry, I said it should be between 1 and 2. 6 to the 1 is too small, 6 to 2 is too big. So it's actually 1.699. Or again, we could just put down 1.7. It's probably accurate enough. And this last one, I'm going to be honest, is a little bit tricky to do because I don't know my powers of 2.5 table very well. I'm good at powers of 2 and 3 and 5 and 7 and all that, but I'm not so good at 2.5s. But just kind of quickly with my fingers, 2.5 times 2.5 is like 6, times 2.5 is about 15. 15 times 2.5 is like 38. 38 times 2.5 is, I don't know, 80, 90-ish, 90-ish. Okay, so 2 to the exponent, 2.5 to the exponent 5 looks a little too small. 2.5 to the exponent 6, I'm sure will be too big. So I'm guessing the answer is between 5 and 6. But I don't need to wonder for too long because I just plug in log of 107.3 over log of 2.5. Log of 107.3 divided by log of 5. And the answer is 5.1 or 5.102, whatever. Either way, I kind of was just taking a wild guess at this one, but I was like, it's between 5 and 6. And yeah, sure enough, that works out. All right. So if we have something like these exponential equations, 2 to the x equals 23. Now these look like the ones we were solving with trial and error, where we guessed an x and then we plugged it in and we were trying to hit the 23. But again, we'd like to be able to do this algebraically. So now we can use logarithms. Now here's the thing. I mean, you can estimate these in the exact same way you estimated the logs because it's still the same question really. What exponent am I putting on 2 to get 23? And we know 2 to the 4 is 16. 2 to the 5 is 32. So it's between 4 and 5. Now the way I would do this one is to just simply rewrite this by taking the log of both, rewrite this in log format. So to take to rewrite this in log format, we say log base 2 of 23 equals x. So again, base exponent answer, base exponent answer, because we're trying to solve for that unknown exponent. And that means that x is equal to log base 2 of 23, which can be thought of as log of 23 divided by log of 2. 23 log. So I have to punch in 23 first, which is why I say it that way. Divided by 2 log. And I get 4.52. Okay, same thing. I'm going to rewrite this. X is the exponent I'm looking for, and it's log base 1.3 of 29. So that's equal to log of 29. Again, the log without any number written as a base is by default base 10, which is what our calculator does. And then I just divide by the log of the base. I will ask that you please make sure that when you're writing these, that you make it clear that the base is a subscript, that it's small and below the log. And so it doesn't look like a log of 1.3. That 1.3 is what you're putting in. It's not a base. Just make it clear which is going in and what the actual base part is. Okay, so this one's the log of 29 divided by the log of 1.3. And I get 12.8. Now again, I could have done this one by kind of trial and error by counting on my fingers, except the 1.3 power table is not an easy one to kind of figure out, as opposed to, like I said, 2 or 3 or 4. But we can use this method just fine. For part C, we've got something just a little wee bit different. In this case, we have an exponent that's x minus 4 instead of just an x. But don't worry about that. Just look at the pattern in the others. The others were all the same thing, where it was the exponent is equal to the log of the base, and then plug in the answer, the 19 in this case. So now we're not solving for x, we're solving for x minus 4, but then we'll just add 4 later on. So this becomes log of 19 divided by log of 5. And plug that into your calculator, and you get out 1.83, I think. Oh, so I don't know why I put an equals there. X minus 4 equals 1.83. And then finally, I'm going to add 4 to both sides and get x equals 5.83. And then you can always quickly double check that if you want. 5 to the 5.83 minus 4, that's 5 to the 1.83, and 5 to the exponent 1.83. It's a little less than 5 squared, is 19.01, which is our correct answer with a little rounding error. Okay, rewrite this one. X equals log base 7 of 150, which equals log of 150 over log of 7. And before I even punch that into my calculator, I know 7 squared is 49 and 7 cubed is like 343, so it's going to be between 2 and 3. And I'm getting 2.57. There we go. These ones with decimals might be a little bit trickier to do, but again, when we're converting them, it doesn't matter. X is the exponent, so that's what we're solving for. And then we're going to do log of 0.2, because it's always log of the number divided by log of the base, and the base is definitely 0.8. If you ever forget which is which one goes on top, which one goes to the bottom is always the base. All right, so the log of 0.8 divided by the log of 0.2 is 0.138. Wait a second, that doesn't seem right. Oh, it's because I said I said the wrong thing. 0.2 log divided by 0.8 log equals 7.2. That sounds better. I wrote it down correctly and then set it upside down. Gotta love when the dyslexia kicks in. Okay, final one. The unknown exponent is equal to log of 0.03 over log of 3, since that was the base. I'm expecting a negative number because 3 to the x would be exponential growth, and it's going to hit 0.03 back before the y-axis. So 0.03 log divided by 3 log equals negative 3.12. 3.19. All right, I think we did it. So at this point, let's go back to a question that may look familiar to you. The percent of medicine in a person's bloodstream T hours after receiving a dose can be modeled by the function m at t equals 100 times 0.71 to the exponent t. I feel like we've seen this before, possibly earlier in the lesson. A doctor doesn't want to give a patient a second dose until there's only 15% of medication remaining. How long must the patient wait before the second dose? So this is exactly the same as the first question we did. Let's see if we can get it a little bit more accurately using logs. So we start off the same way. M at t equals 100 times 0.71 to the t. Plug in the desired amount, 15%, and divide both sides by 100. So this is exactly what we did last time, and then we set up our table of values and did trial and error until we got something really close to 0.15. What we're going to do this time, though, is we're going to convert that from the form that it's in to log form. We know that 0.15 is the answer, t is the exponent, 0.71 is the base. So in log form, we want to find the exponent. We know the base of the log is 0.71. We know the thing we're putting into it is 0.15. And we can rewrite that as log of 0.15 divided by log of 0.71. And when we do that, divided by, we get 5.539193184, which again, just over 5.5, which last time we said it was between 5.5 and 5.6, and that was after 5 trial and errors. Here we basically did 2 extra lines where we converted from exponential form to log form, and then we converted the weird base log into regular logs, and then just plunged into our calculator. So this one, again, I would never actually expect you to write out that many decimal places, but my point is that with the trial and error, every decimal place we want to get means that we've got to do a couple more trial and errors. And here we get all the decimal places immediately using a logarithm. So, moral of the story is logarithms rock for solving exponential problems, and we should use them when we can, except in the questions on the test where I tell you you can't. All right, plenty of practice problems. These ones are probably fairly important for you to try because logarithms are not intuitively obvious to most people. Your brain sometimes has a hard time wrapping around exactly what it means and what the notation is. So practice these, make sure that you can do them. If you're struggling with anything, please let me know. Otherwise, I will see you in lesson 4, which is actually the final lesson of the unit. All right, until next time, have a great day.